Welcome to another episode of the Touring Rabbit Holes podcast, the podcast named in honor of mathematician and computer scientist Alan Turing. This is the podcast where we talk about math and physics and all things that are awesome. I'll say it that way. I'm your host, Gabriel Hesch. I have my master's in electrical engineering. I also taught science for a few years to middle schoolers, science and math, and I love all things science and math. My co-host here is Alex Alanese. You've been podcasting for how long now?
I'd say 4 months, maybe.
Yeah. We have a very audacious goal in today's podcast. Today, we are going to kill Schrodinger's cat and skin it.
Yes, let's skin the cat.
That's exactly what we're going to do. Schrodinger would be rolling in his grave after today's episode. Actually, today we're going to take a look at Schrodinger's equation and also some of the equations that came before his equation. And it raises the question with these equations that came before Schrodinger's equations, how close were these older mathematicians and physicists to actually stumbling on Schrodinger's equation? It's interesting. They were so close. It makes one wonder, why didn't they discover quantum mechanics earlier? You know, there's a variety of answers to that, but we're going to work our way backwards on that. There's something else I'd like to talk about today's goal specifically. Today's goal is to describe everything in the universe in a few simple equations. Because the beauty of mathematics and the beauty of physics is explaining phenomena in simple terms. So in a way, this will be our own attempt at explaining the universe in a few simple terms that you can put in your pocket. So that'll be our goal of today's episode, skinning a cat and explaining everything in a few simple equations. Right. What do you think, Alex? Is that a pretty good?
I think we're ready to go.
Without further ado.
Okay, so the presumption will be that at some point in your life, you've had one semester of calculus, that you've taken a derivative. Mm-hmm. And that's all you're going to need for this episode.
You're talking business calculus or engineering?
Business calculus, high school calculus. Have you taken a derivative once in your life?
Okay, cool.
So, indeed, let's go back. If the world didn't have quantum effects, if it was strictly a classical world, the most compact codification of physics is in the Lagrangian form. Actually, it's in something called the minimization of action. And a guy named Maupertuis, you can look him up on Wikipedia, figured that one out. And the idea is that expression can be turned into Lagrangian formulation. There are many other formulations, Hamiltonian formulation, Hamilton-Jacobi formulations, action to angle variables. There are many formulations, but they are all transformations of each other. So, and they're all equivalent to Newton's laws, F equals ma.
Okay.
So there's just different versions of it. So the idea is to minimize action. Now this explains why if you have a water and air interface and light comes in at a certain angle, it gets bent. It is minimizing action. That is Fermat's principle. So experimentally, we had Fermat's principle before the calculus was invented, I believe, or right around the time calculus was being conceived. We had that experimentally.
Real quick, for our audience members who are not quite following along, I'm tracking. We are going to further define Lagrangian, perhaps who he is. We're also going to further define, who Fermat was, and also the basics of Newtonian physics. So we'll get there. Hang tight.
So you visibly see minimization of action as a ray of light coming in from the air and being refracted by water to a different angle. Mm-hmm. I'll leave it at that. Its formulation in Lagrangian form is you sum up the kinetic energy and you sum up the potential energy. And then that is the Lagrangian. And when you plug that into the integral that you're going to see on the projection, it leads to the Euler-Lagrange differential equation. And I went ahead and did it for the spring.
Awesome. So what we are going to display here in a minute is exactly what Alex said. He actually worked this out for you so you can see it. Now, again, for our audience who doesn't even, because this includes myself, how do you explain what a Lagrangian is and what exactly it does to any set of formulas?
The best way to do it is to actually see it. So let's write the energy equation for a spring that has no friction. So it's a mass m and a spring with a spring constant k.
Okay.
And I'm going to be using Hooke's law from elementary science. And the energy conservation E, capital E, is 1/2 m x dot squared. That's where your derivative's coming in. 1/2 the velocity squared times mass plus 1/2 kx squared. That is the kinetic energy plus the potential energy. And as the spring is going back and forth, see out here, it's all potential energy. The spring is maximally stretched. And as you go this way, it's all maximally stretched. And in between is some partial stretching and partial velocity. And at the very center, it's pure velocity. But in totem, the sum of those two terms is a constant.
And I'm just real curious, who was Lagrange?
He was a physicist and mathematician from the 18th century.
Okay.
And he's one of the many names that were developing mechanics at the time.
Okay.
And so if I plug into the minimization of action integral, I get the Euler-Lagrange equation. And here it is step by step. I do partial of L, partial of x dot. Well, that gives me mx dot. I take the time derivative of that, and I get mx double dot, otherwise ma. And then I take the partial derivative of L with respect to x, I get kx. I plug it back into the Euler-Lagrange equation, I get mx double dot minus kx equals 0. Or, if I just write it in high school way, F equals kx, where F is ma, Newton's law.
Okay.
So you see, I re-derived Newton's law. Now you'll notice that in the Lagrangian, there is no explicit version of time. And guess what? That means that's where Noether's theorem comes in. That means that energy will be conserved.
Okay.
If I were to write an equation of a particle orbiting a star,
Yes.
there would be no theta if I actually write that Lagrangian out.
Okay.
And that would mean that the angular momentum is conserved. Now you see angular momentum conservation at the Olympics all the time. You see the figure skater spinning, and she tightens up her body, and what happens to her rotational speed?
Much faster.
Right, and there's a little friction, so we're violating. If there was no friction, it would be, and she would be able to do that forever and ever, expand and contract and speed up and slow down her rotation. In orbital mechanics, there effectively is no friction out there.
Okay.
And so Noether's theorem is you look at the Lagrangian, and you see if something is missing, that object, that will be a conserved quantity.
I mean, Noether, she was a famous mathematician, I think back when, oh gosh, do you have her
Early
dates?
1900s.
Okay, yeah, and she was actually did a lot of work with Einstein, I believe.
She did a lot of work that underlies our understanding of the universe, of quantum field theories. And I'm not sure if she personally knew Einstein, but she was practicing around that time.
Okay, interesting. Yeah, she's worthy of her own episode as well.
And so literally, if you, I constantly get brand new four-year mechanical engineers coming into to where I work at, and I show them that literally Maxwell's equations of electrodynamics or anything they want, orbital mechanics, can be expressed in the minimization of action. One equation, put that in your pocket, and you have classical physics.
Wow, that's pretty cool.
So what came after classical mechanics? It's a book you made me read.
Yes, absolutely. The book was A Quantum Story, History in 40 Moments by, what was the author?
I forget the author's name.
Sorry, Jim Baggett. Jim Baggett just came to me. Jim Baggett. Yes, that is the book that I refer to as the, I compare it to the Texas Steak Challenge in terms of books. It's a big, meaty book that is basically the entire history of quantum mechanics, starting with Max Planck and the how would we describe the discovery of the Planck constant? I mean, he was kind of, he was just kind of like spitballing ideas to explain some observations in.
Well, there were some contradictory observations in what they call blackbody radiation.
Yeah.
And they had the short frequency domain and the long wave frequency domain, and these two equations couldn't mesh. So he guessed that the harmonic oscillators, in his mind, the atomic model of oscillators absorbing and reflecting light had discrete units. And it turned out that trick, mathematical at the time, was actually physics.
Yeah.
And so there was an experimental matching of his quantized equation, and that's how old quantum mechanics came into existence. And then eventually we get what's called the modern quantum theory.
And essentially, with a lot of what we're going to look at now, it's really a lot of the old equations in classical physics, including things involving symmetry and energy and the Lagrangian version of them, but done with applicability to quantum mechanics, so to speak.
Correct. So now we've compactified all classical physics into a formulation called the minimization of action. in the 1920s, 25, 26, 27, Schrodinger specifically figured out that he could, anytime he saw energy and a Lagrangian, energy being a conserved quantity in this case, he just did a substitution which will project that you do energy, replace it by I, h bar, Planck's constant, over 2 pi, partial derivative with respect to time. And anytime you see momentum, and momentum, so 1/2 mx dot squared can be re-expressed as p squared over 2m, where p is the momentum. Mm-hmm. And then anytime you see p, you do the substitution minus I h bar, partial x. Mm-hmm. You plug those substitutions into the classical spring, and you get a partial differential equation in x and in t. I think we talked about partial differential equations last time.
We did. That was our last episode.
So now you have a partial differential equation, and you have a spatial part and a temporal part, and it's equal to a constant called the energy. Mm-hmm. Well, for harmonic oscillators, we're breathing them in right now. Mm-hmm. You're breathing in nitrogen and you're breathing in oxygen, and those are two oxygens bound together by a spring, or two nitrogens bound together by a spring. And if I were to solve the Schrodinger equation for a spring, I'm going to get the solution is that only specific vibrations are allowed. Either that vibration, the fundamental mode, or that vibration, the second fundamental mode, or the third vibration. Mm-hmm. So if I were literally to heat up the gas in this room and run it through a spectrum, a prism that is, what would you see? Discrete lines.
Yes.
Right?
Yes, exactly. Yeah, in fact, I was trying to explain that whole concept to a friend of mine, and I was talking about, one way to think of it is perhaps barcodes on items at a supermarket. Would you say that's maybe?
It's exactly, and it's a fascinating history, and they're great stuff on YouTube on the history of Bunsen, who did natural gas, and he would stick metals in the Bunsen burner and go, oh, green, that must be copper. Oh, red, that must be whatever metal that is.
Yeah.
And I think it was, I'll have to think of the spectroscopist who came up with this prism, and they mixed them together, and they pointed the telescope to the sun. They go, oh my, look, there's iron in the sun, and there's oxygen in the sun.
Yeah.
And so suddenly vibrational spectroscopy became incredibly important.
Yeah.
Historically. Now, it might seem like magic. Take a classical equation, and anytime you see energy, change it to the substitution I told you, and anytime you see momentum, change it to the substitution I told you, and you get Schrodinger's equation. Mm-hmm. In actuality, as you pointed out, in I think the 1830s, physicists had derived the Schrodinger wave equation in a wave mechanics, classical mechanics formulation. Mm-hmm. They had no experimental reason for accepting that.
Yes. And what you just said is actually one of the reasons why I like podcasting. It's the fascination of being able to discover new things where you're playing around with mathematics and something suddenly pops out that later you have experimental evidence to verify. And that is the amazing predictive power of mathematics.
So as we promised, a universe in a pocket, right?
Yes.
You have the minimization of action, and you have these substitutions, which give you quantum mechanics. That's non-relativistic quantum mechanics. And you don't need relativity for ordinary chemistry.
Yes.
The energy levels of the shells that you're used to seeing since you were in elementary school, and why they're specific shells, come from the Schrodinger equation. Mm-hmm. So now we've covered almost the vast majority of the observable universe with just two ideas.
Yep.
The next thing was Einstein did special relativity, which is that the speed of light is a constant no matter how you're moving. It's always going to be a constant.
Yes.
And so that modifies classical mechanics into a special relativistic mechanics. And I'll try to do it in the air here, time dilation. If the speed of light's a constant, and I start off with two clocks with lasers going like that, and they're synchronized.
Yes.
And I grab this clock and I put it on a choo-choo train, because that's what they used to do in the past, it now does that. Mm-hmm. And so the time it takes, because the speed of light's constant, for a tick-tock is longer if I'm sitting on the ground with my clock here and I'm watching the train. Time is going to be dilated on that. And so it modifies classical mechanics, and we get the famous equation that E equals mc squared. Mm-hmm. So now if you go back and you write a Lagrangian that's relativistically correct,
yes,
and you do the quantum mechanical substitutions, you arrive at quantum electrodynamics. And the beauty is if you write an equation that describes the electron, and you say that's relativistically invariant because I'm using special relativity, you should do one check. You should do a Lorentz transformation on it and see if indeed left equals right.
Yes.
It doesn't for the Dirac equation.
Okay.
You have to muck around and add terms to the Lagrangian until finally you get the transformation. The Lorentz transformation gives you the same as what you started off with after the transformation. Those happen to be Maxwell's equations.
Yeah.
So that principle is how we figured out the electroweak force, the strong nuclear force. So now we're up to 3 ideas. Minimize action. Do those conversions to get the quantum mechanical equation. Upgrade to special relativity, repeat, and now you get quantum electrodynamics and a way to get the other forces of nature that we know to observe in accelerators. That's pretty amazing.
Yeah, absolutely.
And so that's it. That's the universe in a nutshell. The mathematicians have generalized that even further. That includes general relativity with fiber bundles, and you can explore extensions of our universe that may or may not be true.
Yes.
That our universe may be a part of an extended theory, or there may be other universes in a multiverse scheme that are described by this mathematically generalized thing. Now, what do we say we're going to do about the cat?
We're going to talk about Schrodinger's cat. We said we're going to skin the cat, actually.
I have never been happy with the thought experiment of the Schrodinger cat.
Okay. And just for our audience who may not have heard of the thought experiment, super quick. This is an idea that brings together or that tries to explain the wave function and the dual nature of waves and or particles that we seem to observe based on experiments. And the idea is that when something is not observed, it exists in a wave, and that when something is observed, it exists in a discrete particle in one position or another position, but not both.
So the Schrodinger cat, you put a poor cat, a thought experiment cat, in a box with a poison vial and a radioactive atom, and the atom obeys quantum mechanics. And then you close the cat into the box, and the paradox that Einstein was trying to point out at that point in his life when he doesn't like quantum physics anymore is that, come on, tell me, Bohr, the cat's alive and it's dead. And Bohr would answer, why
correct. Yes, it is both alive and dead at the same time because we haven't observed it. And again, what we're saying is with the poison vial and the radioactivity, if the radioactive element shoots off a proton or an alpha particle or whatever, it'll be sensed and the poison will be released.
Right.
Now, if we don't observe it, we don't know whether or not that has occurred. And in quantum mechanics, as an observation has not been made, the thing that was not observed exists in all possible states. That is to say, the radioactivity both emitted and did not emit radiation, and the poison was both released and not released, and the cat is both alive and dead. Very, very weird, very, very strange implications here, but that is correctly what quantum mechanics predicts.
So let's peel away that mystery.
Okay.
Everyone's probably been to the beach or to a river or to a swimming pool, and you know that waves add.
Yes.
And they add linearly. If 2 peaks meet, you get twice the peak. If 2 troughs meet, you get twice the trough. If a peak meets a trough, you get nothing.
It cancels out.
They cancel out.
Yep.
So imagine this experiment, the double slit. Let's imagine yourself in a very large swimming pool, and I'm going to create a wall, and I'm going to pierce the wall with 2 slits.
Yes.
I'm going to have a person stand 10 meters back and start splashing, not splashing, but pounding the water. Pounding the water at 1 hertz. And you're going to see these spherical waves expand. And by the time they get to the wall, they're pretty planar. So
yes.
You can treat them as plane waves.
Yep.
And it will the plane wave will impinge the wall with the 2 slits. And from the 2 slits, you're going to get brand new spherical waves like that.
Yep.
If I can do that. And they're going to add in a triangular, they're going to add in the center additively, then they're going to be, at a certain angle, they're going to completely cancel out, then they're going to add up again, but not as much, and then cancel and then add. And that makes sense in water.
Yes.
Let's go back to a single electron. We're going to create a double slit, and the particle, an electron detector,
Yes.
And we're going to have an electron gun, and we have the technology to squirt out one electron at a time. It's going to go and impinge the screen, the detector, as an electron. Ping, it will make a detection.
Yes, a single discrete electron.
And then you keep doing it, and you keep doing it, and you keep doing it, and you're going to get the same wave pattern as if it was water.
Mm-hmm.
And so what that's telling physicists is that when the electron leaves the electron gun, it's being described by a wave function, much as the person doing the 1 hertz on the water, and they're spherical, and they eventually become planar, and they eventually hit the double slit and start off as 2 spherical waves. The electron from the electron gun begins as a spherical wave in a medium, and I shouldn't say medium because that's really bad physics, the ether. Anyways, they get to the electron wave function gets to the double slit, and splits up, and you get interference patterns. And the electron will obey those interference patterns. It will most likely appear in the central peak or in the 2 side lobes with a little bit less probability, or on and on. So while the wave function that got split up by the double slit, while that compounded added wave function is propagating, that is a Schrodinger's cat. That is an electron that is simultaneously part of, I'm going to hit the middle, simultaneously I'm going to hit the top and bottom lobes, or the next interference pattern lobes. And not until you open the box, or not until the electron smashes into the detector, does that wave function collapse back to a point. So while it's in progress, it's a Schrodinger's cat. I don't know if it's going to go up or down or hit the center until I observe it. That's the cat.
Yeah.
So the cat is not as mysterious as a real cat sitting in a vial, sitting in a box with the poison, and the poison will be triggered if the uranium atom decays. But yet that cat's still true. I mean, the macroscopic cat, it's still true, as you said.
Yes. So is the cat alive or dead? That's what our audience wants to know.
It is both.
Yes.
And that is the answer, until you observe.
Yep. Wow, quantum mechanics is really weird.
So that, we promised, is the universe in a pocket. That's how, if you really want to compactify what physics is, that's it.
Yes.
Minimize action, convert it to a quantum mechanical equation or a special relativistic quantum mechanical equation, and you're done. I think we've met our goal.
So if you would like to reach out to us, of course, you can comment in the comment section. You can also shoot us an email at touringrabbitholespodcast@gmail.com. Gosh, where else? We're also on Instagram, Touring Rabbit Holes on Instagram, so you can find us there. So if you have a science concept you'd like us to discuss, or a mathematical concept, or anything involving symmetry, or the standard model of physics, or anything else, let us know. And we'll perhaps it'll be on an episode. So
okay,
all right,
awesome.
thank you for joining us. All right.